when I prepared this talk, I will present some of our research, but I wanted to present this as a little more of a philosophical discussion on what is science around water. Because this is the Bangalore Science Gallery, I think that it's useful to reflect on what we mean by science, because it sounds like an obvious question, but it's actually not that obvious when you're talking about environmental sciences in particular. Does anybody want to tell me what their idea of what science is? I mean, what's the picture of science that you have in mind? Does somebody want to hazard a guess? Anything. I mean, there's no wrong answer to this question, so you can literally say anything. Experimentation, right, perfect. And that's how we kind of learn science in school, right? You basically go to science lab, you have a hypothesis, you collect data, you get results, and then you conclude if your hypothesis is correct or wrong. Now, when we study watersheds or river basins or even the global planetary system, there's no question of doing experiments, because you don't have two Earths and then you do something on one Earth and then, you know, keep the other Earth as a control, right? I mean, that kind of approach of Popperian hypothesis and rejection of the hypothesis doesn't apply. So then what is science in that context of environment? Similarly, it's equally true of the river basin, right? If I'm studying the Kaveri, I don't have two Kaveris where I have people do something in one Kaveri and people not do it in the other Kaveri and then see what the difference is. So the concept of experimentation, which is the way we are taught to think about science, doesn't apply in most of our environmental sciences. And so then the question is, what is science in that context? So I'll start a little bit about what the history, at least for water science, and I come from the point of view of hydrologic sciences, which is the quantity part of science. I'm not going to talk much about water quality today, but some of these ideas kind of apply equally to water quality. So why did water science, I mean, why is it even a science? It's not biology, it's not chemistry, you know, it's not physics, it's not a fundamental science. So what do we even mean by science in the context of water? And in this case, I'm talking about hydrologic sciences. What does that even mean? And so traditionally, the purpose of science in these kind of applied areas like hydrology was a very, very instrumentalist one. It was basically, you know, there are people, I need to deliver water for irrigation, I need to build a dam, and so I need to know what should be the dam height so that the dam doesn't break, how much water will I get, how much water will it store, what should be the canal sizes that I can bother to build in order to deliver water. If it's an embankment, I want to know how big is the flood size that I should plan for. On that side, I've drawn what's called a culvert, the thing on top. This thing is called a culvert. Unfortunately, you don't see more of them in our Indian roads, but basically, if a road crosses a stream, I need the stream to flow under the road because there's no point in streams flowing over the roads. Even though you see that in India, it's just going to erode the road. And so you need to know what size do I build these pipes. That's called a culvert. Or if you have a stormwater drain, again, something we don't see enough of in our Indian cities. But basically, I need to make sure that when it rains on cities, the water is kind of drained out and goes to some lake or something. And so I need to have a sense for that. So traditionally, the purpose of science was very clear. How do I estimate that when it rains X, how much is going to show up in the stream and where? So this kind of, if any of you are engineers, are any of you engineers? Okay, couple of people are engineers. The very first, second, third year of engineering that you do, you would have studied something called a unit hydrograph. And a unit hydrograph is kind of, you know, the basic building block of this kind of engineering science, which basically says if it rains this much, then, and this is in the rainfall in millimeters, what's going to be the size of the flood peak, and what's going to be the time lag between when the rain happens and when the peak discharge happens. And this kind of question is, and then once it peaks and drops off, how much is it going to drop off to? And it's a very, very engineering-based calculation, right? So actually, thus, a lot of water science or hydrologic science was actually hydraulic engineering. That was the purpose of it. Let's find a bunch of equations which I can plug in so that when I stick the rainfall into it, on the other side, it's going to tell me how much my stream flow is going to be, how delayed it's going to be, what the magnitude is going to be, and so on and so forth. Now, as computer simulation in the 70s became more and more and more sophisticated, we could move away from the rules of thumb that we used to use. So if you went to the 1950s and 60s and you worked in a civil engineering firm or a government department like the PWD, you would have these massive rule books, and the rule books would tell you this is how you translate the amount of rainfall into the amount of stream flow. This is how you translate the amount of rainfall into a culvert size. So it would be very much based on these very simple empirical rules of thumb. Now, as computer modeling became much more sophisticated, we could specify these watersheds and these equations in much more complicated ways. So you could have a whole bunch of input. You could say, you know, I'm going to give literally spatially specify my precipitation, my soil, my land use, and so on. And then what it would chuck out the other side is a spatially disaggregated stream flow or runoff. So I would be able to do much more sophisticated stuff. Now, the problem with this kind of modeling that emerged in, say, the late 70s, 60s, 70s, 80s, 90s, and to the present, is that I don't actually know what the soil is in every square inch of my watershed. I can measure it here and there, but it's not physically possible if I have a 10,000 square kilometer river basin for me to know what my soil is in every square meter of that. Can I know that? I can't. I mean, I can guess what a soil map is and so on, but I still don't know the soil properties. And if you think about it, watersheds are pretty complicated things. I mean, you know, rats and beavers build dams. I mean, there's a whole bunch of small stuff that happens, and all of that contributes to a ton of heterogeneity, so that every square meter of my 10,000 square kilometer watershed actually has something going on at that scale. And so I never, even if I went and looked at every square, it was physically possible, the amount of measurements I would take to be able to physically model my entire watershed would be insane. And yet, today, most of our watershed, the direction our water science has gone in is basically to harness the power of computer modeling and get more and more and more and more sophisticated in terms of the number of parameters I measure. I throw sensors everywhere, I get satellites, I kind of measure everything in every square centimeter, and then that gets me better and better and better at my model. Now, the main step in our modeling process when we do this is that we don't actually know what, like I said, the measure is. And so eventually what we end up doing is we make guesses. And this is called a process called calibration. I don't know if any of you have heard of this concept called calibration, but bear with me for a second. It basically means that what I do is I start with an initial guess value of what my soil is, what my interception is, what my infiltration is in every square centimeter of my watershed. And then I put those into the equations, and then I see how well I do in comparing the runoff that my model generates with the real runoff. And then I keep on adjusting all of these things until the two of them match. And then I say, okay, now I figure out what's happening in my model. Now, I don't know if any of you are getting the sense, and then what I would do is I would calibrate it, and then I would run it for half the data that I have, half of my stream flow record. And then for the rest of it, I would just run it without tuning the parameters anymore. And then I would see, does it still predict what the real stream flow is? And that would make me say, okay, I have a reasonable sense of what the model looks like, okay? Now, the problem with this kind of thing, particularly in our Indian watersheds, is that if any of you live in Bangalore, you know that nothing stays fixed for long periods of time, because constantly everything is changing. People are building new roads, you know, new irrigation is coming up, new diversions are coming up. If you ever worked in any of the lakes of Bangalore, you'll know that they are incredibly dynamic systems. BBMP will come and, you know, it'll dump debris in one stormwater drain one day. The next day it'll excavate it. Next day somebody will, you know, JCB will come and they will break the bund of Hulimau Lake. So if you're trying to actually model any of these things and you had measurements even, the system isn't even staying the same. What are you going to measure, right? And so it becomes a really, really complicated thing to have this kind of static assumption that I'm going to basically take my stream flow record, tune these parameters for half of it, and then run it for the rest and see if it checks out. So the main problem that hydrologists have identified in the last 20 years or so is this kind of tuning. The problem is there are so many parameters in a watershed that literally, and all you have to check if your model is correct is a couple of, maybe you have a stream flow record and you have some groundwater measurements, and you can check the observation against what your computer model gives you, and then you're making a judgment of is that correct or wrong. But most of it, the problem is that hydrologists found that there are many sets of parameters that all give you the correct result, right? And so the problem is this entire superstructure in which we built our science is actually nothing better than curve fitting at some level. Because I have only very few points against which I can test whether my model is correct. But I have many different models that can fit those few points, and I don't know which one of them is correct. And there's plenty of research which have shown that if you take 4 different people and ask them to build a model of your watershed, they'll build 4 very different models, all of which will replicate your historical stream flow. None of the 4 models are remotely similar to each other. And hydrologists call this problem equifinality. So the problem is, what do you do in this situation? And to bring you to this point, I just wanted to get you to the feeling that all of our we start off with an idea of what science is, which is this conjecture refutation idea that you set up a hypothesis and then you reject it. None of that is what we are doing actually in water science. And so the problem is, how do you fix something like this? Because like I said, the idea that we had, our philosophy of science, of conjecture refutation, doesn't work in these complex environmental systems. So then how do we start developing a scientific structure for science? And unfortunately, I would love to tell you that we've figured this out, but we haven't. And that's where I hope that your generation will begin to look at this problem afresh, saying, let's really start with what fundamental principles, what we mean by discovery of something new, how do we get there, and then how does that make us answer questions that we really care about. So, as I said, one of the problems is, of course, that a lot of what we do is just curve fitting, because a million different models will all fit the handful of data that you have. The other problem is, from the very instrumentalist side, it worked very well when our job in water resources was only to build structures. As long as the purpose of hydrologic science was to build dams and build canals and build culverts, that very simplistic approach worked. But today, the kinds of problems that we are encountering in water science are much more complicated. And these are just kind of questions that I might have pulled out of newspapers or newspaper articles, where they're asking a scientific question which is of societal relevance, but the framework that I just presented of our water science isn't going to get me to answer this question. So if I want to ask the question, why did the Arkavati River dry? Or why did Chennai have that severe drought and Bangalore not have a drought? Why will planting trees along rivers for a 1 kilometer buffer restore stream flow? How can I stop my borewells drying or having to go to 1,000 feet for groundwater? If you've heard of Prosopis juliflora, it's this highly invasive species. Why is it taking over our water bodies? How come the Kaveri flows throughout the year even when it only rains a few months? If you ask questions like this, the kinds of approaches I talked about don't actually get you to answering these questions. And so we are faced with this issue that we have a bunch of questions that require science, but our science doesn't get us to answering that question. And so how do we solve this problem? So I'm going to give you 2 stories. I'll give you a framework, and one problem, of course, is that, like I said with the modeling, that often we believe our models so much that, and a lot of water scientists don't go to the field and actually check if anything they're doing remotely resembles anything that's in the field. So that's one problem. And so you built a model, and people fall in love with their models. So after some time, they believe that their models are reality, and reality isn't, somehow their models are more real than reality. And that's a real problem. The other problem, of course, is that they're not being pushed by a lot of policymakers, because oftentimes the policy side of the dialogue is driven by politics and considerations other than science. And so often, and by the way, these are all real life cartoons, okay? They're all actually based on conversations. But basically, often the policymaker in this case will say, we'll support your research, but you have to show us that, you have to tell us this answer, right? And so both ways we have a problem, where the science isn't giving us the answers, and society, or at least the policy-making part of society, isn't necessarily wanting to hear the right answer. And so in this kind of a framework, how do we develop a new framework for science that's actually useful, socially relevant, answers the kinds of questions, and is based on a philosophy of science that has some basis? So I'm going to propose that one way that we ought to be going about it is to start by these puzzles. And a puzzle is a good way, a puzzle is a good way to start, because it tells you, what is it that I don't understand? A puzzle is something that I encounter in the real world, but I'm not able to come up with a simple explanation for. Okay, so I would say start off with a puzzle. You collect data and then observe patterns, and you kind of say, do these match the puzzle or not? And finally, then you infer processes from these. Now, this is a form of conjecture refutation. It's not different, but it actually allows not only a simple statistical set up a hypothesis, null hypothesis, and reject or accept. There are ways to do models as well that still do that. There are ways, so it allows you to develop an ensemble of different approaches or methods that will suit, depending on the complexity and the number of confounding variables and so on. But it allows you to actually start from something you really care about and say, can I come up with a process that will answer that question that I posed to start with? So I'm going to give you 3 examples from our work at A3. Not all 3 are mine. One is from Jagdish, who you heard the other day. Some of you might have heard the other day. This project was in the Arkavati Basin. If those of you don't know what Arkavati is, it's the river to the west of Bangalore. It starts in Nandi Hills. This is the Arkavati. This is the Kumadavati River, and they both meet at the confluence, which is the Tichali Reservoir. And the Tichali Reservoir was built in 1937, and it was one of the big water supply reservoirs for Bangalore. Now, when we started doing this project, it was about how do we find approaches to adapt to climate change better. And as you know, there's a lot of concern about climate change, and there's a lot of investment, particularly in the water sector, which basically says that how do we manage our water assets better so that we are more resilient to climate change. And there's a ton of research and a ton of money going into this kind of thing. So when we started, we said, okay, very first thing, let's say what the climate models are saying about what's happening to the Arkavati. And happily, it said that average rainfall was going to increase, right? So great, end of story, everybody can go home, we're dry, we're going to be less dry, no problem, right? Except, when we looked at the stream flow record was going in exactly the opposite direction that the climate projections were saying we should be going. Climate projections were saying that we were going to be facing a wetter future, but there had been an 80% decline in stream flow into TGLE reservoir. And so you have this, one of the two's got to be wrong. Either your data is wrong or your climate projections are wrong, or your relationship between climate and your stream flow is wrong. One of the 3 has to be broken, right? There can't be any other explanation. So this is what we started off looking at. And the second thing we found is that of course, one thing with India, I'll tell you in general, and you'll see the data that I use here is often highly mixed, because the thing is that you never have enough data to answer anything that you like. And so one of the things that I would say is throughout is that we have to scrounge for data. Like some part of it we get from satellites, some from secondary data, some from farmer survey data, we use sensors, we use everything. But when you put all of that everything together, consistent pictures do begin to emerge. So I think that if you're doing environmental or water science in India, definitely just looking at one type of data is not something that that's not what I personally subscribe to. So the other thing we did is we said, okay, what does the annual season crop report say? Annual season crop report basically has something called the sources of irrigation. And it basically said that by the early 1990s, firstly, surface water irrigation had disappeared. This is tank irrigation. And everything became groundwater. And moreover, by the mid-1990s, open wells had disappeared and everything became bore wells. So very clearly, there's this thing that happened in the 1990s, early 1990s, which is that basically all of your surface water had disappeared by then, and all of your shallow groundwater had disappeared, and by the mid-1990s, we had moved to bore wells. So pretty much that's a clear thing. So your surface water disappeared and your groundwater disappeared, long and short of it. So he said, okay, why did that happen? And we put every possible hypothesis we could think about. We said, is it raining less? Is it getting hotter? Is it that we've put eucalyptus in there, so the eucalyptus is sucking up everything? Is it that we are pumping and putting these bore wells, and the bore wells are drawing down the water table? And when you draw down your water table, what happens is that instead, when your water table is shallow, your groundwater seeps into streams, and that's called base flow. Now, that's the reason why large rivers like the Kaveri flowed throughout the year, because if it only rained from, July to December to November, why would the Kaveri flow in April and May? But historically, these were perennial rivers. The large rivers were perennial, even in south, not the snow-fed rivers, but even in south, our rivers were perennial rivers. But why would that happen? And that happens because of this phenomenon called base flow, which is that the rivers soak up the rain essentially, and then they ooze the rain into, ooze that infiltrated rainwater into the stream in the dry months through a process which we call base flow. And that's what keeps the river going for the dry season. Now, what happens is when you draw down the water table, instead of the blue, which is your aquifer feeding your stream, your hydraulic head actually gets reversed, and your stream begins to feed your aquifer. So not surprisingly, when you overexploit groundwater, your surface water will also disappear, which is what we've seen in all of these places. So that was the next explanation. And then the final explanation was maybe we've just put so many of these structures and roads and stuff all over the place that the water is just not reaching the stream, and it's kind of getting stuck here and there. I call that the million puddle theory, just to say that instead of having one big tank, you have a million small things which are dispersed here and there because you've lost the connectivity of the watershed. Now, I should specify that the results here are only for this watershed, because I myself have worked in watersheds which have alternative explanations work out. But the long and short of it is we could not find any evidence that it was raining less. So we did all the statistical stuff. We did the annual rainfall, we did the daily rainfall, we looked at intensity, we looked at everything, and there wasn't any significant statistical trend, and certainly not anything that could explain an 80% decline in stream flow. There had been no upstream dams. Another way that you see rivers drying downstream is you built another dam upstream. That didn't happen either. We looked at temperature. Temperatures have gone up, but not enough to drive anything, because cloudiness had also gone up and the two kind of balanced out, and so we didn't see a significant change in what we call potential evapotranspiration, but don't worry about that. But nothing that would drive that kind of drying. So it had to be, these three explanations, which are all anthropogenic modifications or human modifications of watersheds. And it's important to realize this because in our field, in the field of hydrology, humans don't exist. Humans don't do things. It rains and the water shows up in the stream, or it rains and the water shows up in the river. Humans altering stuff in between is not something which is part of this entire field at all. And so now you suddenly have reached a point where you've asked an important question that everybody cares about. It's a question that only science can answer, which is why did the river dry? Yet, unfortunately, the causes of that lay outside the natural world, and it lay in the human world of what humans are doing to mess up the entire thing. And this is an important theme that I want to understand because it makes life really difficult. That's not the way we've set up science. We set up science as you have natural science, you have an Indian Institute of Science and an Indian Institute of Technology. You don't have sociologists sitting there. So you don't have, we've disaggregated our research by universities into nice boxes, where now suddenly the world is throwing up something where everything's mixed up, and how do you answer this question? So when we did this, and I should say that when we did this, we do this as team science. It's not me. I should be really clear. This is not my work alone. It's the work of an entire team. And the team consisted of people with very, very different backgrounds. So we had a sociologist, development studies person. I was the hydrologist. We had a person who had expertise in land use, land cover. We had an economist, and we had a water quality person, all working on the problem together. And therefore, the kind of insights you can get when you work in collaborative teams is a very different kind of science than the kind of science we think about where people work in a laboratory and then have their eureka, they have a hypothesis and then they do an experiment by themselves, sitting alone at night, and then they have a eureka moment, right? And that does happen in a lot of other sciences, but when you're dealing with large landscape scale changes and you're asking questions at that scale, it's rare that you can work with one field and one individual scientist. And so this is a very different paradigm shift in the way we need to be thinking about science at all. So the first thing that we did is this insight came from our social science colleague who did farmer surveys and focus group discussions and that kind of thing. And basically, they found that because Bangalore was growing, urbanization induces farmers to intensify, and they either drill deeper and go and move to commercial agriculture, or they abandon agriculture and put their land under eucalyptus. So this is a behavior, an underlying human behavior that the social sciences tell you what's happening in response to some of the larger drivers in the landscape. And so you can look at it 1972, 1973. This is from remote sensing. Everything is looking like it's rain-fed ragi, except in the command areas of the tanks. These are the tanks. And if you know Indian systems, you'll know that the tanks were historically built as what we call cascading tank systems. That means the tanks are built on the stream, and when one fills up, it overflows and goes to the next, and then to the next, and then to the next. So this is what it was like in 1970. The only place that farmers were able to irrigate was in the command area of these irrigation tanks. Then by 1993-94, suddenly those red irrigated areas or double cropped areas had kind of bled outside the tank, right? It's now suddenly everywhere in the landscape. Why does that happen? Anyone wants to hazard a guess? What happened between 1972 and 1992? Canals, I heard something else? No canals in this place. Bore wells. So the main thing that happened is that bore well technology suddenly became cheaper. There had been some major revolutions in bore well technology which made drilling much, much cheaper. Now, what happened, of course, with the wisdom that policymakers had at that time, firstly, they gave electricity free in the early 1980s. The second thing they did was they started a lot of bore well loan programs, and they did that in all their wisdom, because if you think about it, this kind of a system where only a few handful of farmers have access to irrigation is a very inequitable system, because everybody else is growing rain-fed ragi and a handful of farmers basically have a chance to grow rice. And therefore they are wealthier, and there are other issues of caste and so on that are also connected. But the minute you do this, you've suddenly, what bore wells did is they democratized water. They allowed anybody who could take out a well now. They didn't have to belong to that particular landowning caste which was in that command area. Now anybody could access water. Not surprisingly, everybody started doing that. Then, of course, by early 2000s, people had changed what they were irrigating for. You can see a lot more of the greens, which are basically your coconuts and areca nuts and vegetables. They are your annual irrigated crops. And then a lot of eucalyptus, which is the purples, have started coming into the catchment. And then, and as I said, the eucalyptus, because farmers started following this go big or quit strategy. They either drill deeper and grow commercial vegetables and so on for Bangalore, or they put their land under eucalyptus and go work in the city. And then, of course, that trend continued, and then you can start seeing Bangalore itself starting to encroach into the catchment, right? Okay, what was the second thing that happened? As that happened, not surprisingly, both bore wells as well as eucalyptus causes the groundwater table to drop. Eucalyptus is a very water-intensive plantation. And so the next thing that happened was so groundwater levels began to dip. And the first thing that happened was that watershed development started happening, right? People started putting check dams and farm ponds and stuff. All kinds of measures were taken by the Gram Panchayats and by the Zilla Parishads and the watershed department to reverse that groundwater depletion. So what did they do? They found different ways of taking water in the streams and sticking them into the ground, or taking rainwater and sticking it into the ground. That's the long and short of what they started doing. Now, what did that do? If you've ever seen a check dam, it's basically a wall on a stream, right? And what they basically did, we basically mapped all the check dams and so on. And we found this was the partitioning of the water that flowed into the check dam. P is in percolation into the ground, E is evaporation, and O is overflow, which goes downstream into the next check dam or the tank. And you find that about 15 to 20% of the water evaporates, and the rest of it more or less percolates. And the long and short of that is basically check dams do what they're supposed to do. They take rainwater and stream water and stick it into the ground, right? But if you take stream water and stick it into the ground, what's going to happen? You're going to have less stream, right? Not surprisingly. And yet, 99% of our rural development programs are pretty much on just based on this principle saying groundwater is depleting, so you got to recharge. And how do you recharge? You're not creating new rain. You're taking water that was in the stream and sticking it in the ground. This is fine if water was, and Jagdish just gave a talk on Sunday about why it's wrong to say water was flowing uselessly to the sea. But even if the water was going to the sea, that would be okay. But when we are sitting in the middle of Bangalore, there is no water, there's no sea here. None of this water was going to the stream. Every bit of water that was going downstream was being used by somebody else. So any water that we take upstream and stick into the ground is water that's not going downstream. And so you immediately have these tensions of upstream, downstream. Whereas where it's already a fixed pie, no water was crossing TG Halli anyway. Since 1937, barely any water was crossing TG Halli. Maybe once every 15 years, some water was going downstream. So the other 14 out of the 15 years, the water was pretty much, all the rain that was in TG Halli was being used in the TG Halli catchment. Now suddenly you started pumping the heck out of groundwater in different places and stopping the rain and sticking it into the ground to make it up. Well, not surprisingly, the water is not going to reach the stream, right? And I'm kind of, we have like a ton of isotopic data and this and that. I mean, I'm skipping over a lot of measurement and modeling work here, but take my word for it. I mean, logically it should make sense to people. This would be interesting if, it would be uninteresting if everybody already knew it, yet that's not the assumption based on which all of our programs are run. So this is kind of a question where we do science, but the science is actually questioning how we manage the system, right? It's changing that. Okay, you're sticking the water into the shallow aquifer, but you're drilling from you're pumping from the deep aquifer, and so we needed to also show that the shallow and deep aquifers were connected. Firstly, we need to show that the deep aquifers were getting depleted, so this was some of the work we did with asking farmers about the depth of the wells. I just thought it's interesting to show you this because even though the wells are getting deeper, these are a histogram of wells by decade, you can see they're getting deeper, but they're also more and more at the same time. So you can see you're simultaneously intensifying while you're depleting, which was also not obvious, right? It could be that as the wells got deeper, everybody just gave up and went home. That clearly didn't happen. We also did a ton of these camera scans. Again, I won't go into the details on the camera scan work, but the long and short of it is you see that element of connectivity where the water from the shallow zone is cascading down into the deeper fractures. And we have a lot of other isotopic work also, but the long and short of all that work is it tells you that the shallow and the deep zones are well connected, which means that the water that you're sticking in the shallow zone is going all the way down, it's going to your deep zone, and then you're pumping it back up. Now, if you think about it, that's pretty insane because you've created this huge depletion. You're sticking the water in the shallow zone. You've now done all kinds of watershed development to stick the water in the shallow. It's going all the way down, and then you're pumping it all the way back up from 1,000 feet. So basically, it's pretty crazy the pretty crazy way of managing the system. I can answer more questions there. But the long and short of it is then we found that the long and short of it is where does the rain go? It's still raining as much as it did. Where is it going? Well, it's going into vegetation upstream. The water that would have flown into the reservoir downstream is being trapped and used upstream, is the long and short of it, right? Okay, so what does this all show us? This entire thing is now an emerging field called the field of socio-hydrology, which is basically saying that when you live in watersheds where there are also people, you can't pretend that the people don't exist. You need to assume that the people are going to change those governing equations that we used to use in our models. And the people do, when people change governing equations and models, they don't do it in a linear fashion. They do it in a way that actually alters, they do it reflexively. That means in the sense they're actually seeing what's happening and constantly tinkering with the watershed, which means it's a much more complex field, and it's a field that you need to understand what are these ongoing feedbacks between the water system and the human system. And it's not something that I can just do a simple linear equation saying this is how humans change watersheds and you're done. Does that make sense to people, that this is happening as a kind of a constant adaptive process? Yeah. And that makes the philosophy of science and our ability to study this so much more complicated. Because not only does your system have 1,000 different parameters, everything's changing all the time, but everything's changing all the time in unpredictable ways. And so I need to have a way of kind of bounding what things are important, what processes are important, and what processes, how humans are changing in response to what's happening in the water system and vice versa. Okay, the second question, and I'm going to skip through this really quickly. Why did Chennai shut down during the drought? And I only put this in here because it happened so recently, right? But when I studied this, this was in 2003, 2004. Everybody knows where Chennai is. And this is what happened in 2003, 2004. And does this sound familiar? Right? This is exactly what happened. History repeated itself this year. People forget, because in 2003, 2004, there was no such terminology called 0 day. So when people would, talk about Cape Town and 0 day in Cape Town, the first thing you would say is, wait a minute, 0 day happened in Chennai in 2003, 2004, and it happened for an entire year. We had 365 0 days in 2003, 2004. We just didn't have the word for it, and it's kind of become normalized because Chennai is always going through drought, and so we just kind of, don't have words for it. But at that time, basically, what the water utility wanted to do is build lots of desalination plants. The World Bank was saying, not unreasonably, that basically if you give unmetered water, people are going to waste it, and your pipelines are very leaky, you got to fix them. So that's what the banks were, that was the position. And then the NGOs were saying, you should do rainwater harvesting. All of which are not unreasonable solutions to a crisis. The question is, which one? And should you do all of them? And are there any trade-offs between them? Now, it's really important to realize, how many of you heard in this drought, how many of you knew that Chennai had a drought this year? Okay, everybody heard that it was in the news. How many of you heard that Chennai should do more rainwater harvesting when there's a drought? Many of you, right? About 60% of you. So the question is, and here's my question to you, which is, when your pipe supply system shuts down, your pipe supply system is supplied from a reservoir, right? You're doing rainwater harvesting in your house. The reservoir system is way outside the city. It's not in the middle of the city, right? Your water supply reservoirs are not in the middle of the city. If you do rainwater harvesting in your house, is it going to put water into the reservoirs? No. And so this doesn't mean that rainwater harvesting is a bad thing, but it's not going to stop 0 day as long as we realize that. Those are two completely different systems. Now the question is, you have a set of interventions that people are proposing. They actually impact completely different parts of the system. So the supply augmentation, which is to bring water from Viranam or Mettur or build new desalination plants, is got something to do with the whole reservoir system. Your efficiency improvement has to do with the pipe supply system. And your rainwater harvesting has to do with your local aquifer in the city. And these are not even connected systems. They are not connected systems physically. They are even less connected in terms of scientific research and in terms of policy. There are different agencies that manage them. There are different disciplines that study them. And so then how do you navigate these kinds of questions which involve claims which are made from very different scientific disciplines? So the question about this is an engineering question, which is, if I invest X in retrofitting pipes and change from this type of pipe to that type of pipe, how much will the pipeline leakage decrease? That's an engineering question. If I say, if I increase my price X from X to 2X, how much less will people consume? That's an economic question, right? That's a demand and supply curve. If I ask, should I build a desalination plant? That's again an engineering question. There may be an ecological question to say, are desalination plants going to create dead zones in the sea or whatever? There may be some associated questions there. And then this is a groundwater question, which is a hydrogeological question. And how do you then answer questions like this? And so one of the challenges that we did here, that I did for my thesis work, was basically saying how do we kind of look at it in a conventional way. And one of the ways is that you build these system maps in ways that bring all the pieces together. I won't go into the detail, but this is how people traditionally think about urban systems, that you have a water utility, it gets water from reservoirs and groundwater, and it supplies it to a consumer. That's kind of the engineering way of looking at urban water supply. What happened in specific is that it wasn't even beginning to explain what happened in Chennai. What happened was that 66% or 70% of the households had their own wells, and then a large part of the city was also able to call private tankers or public tankers to deliver water. And that was a significant fraction of the water that was coming, which means that traditionally the way we approached problems like this, which was through engineering and modeling and understanding water utilities, had nothing to do with where the water was actually coming from. Which means that if I wanted to understand Chennai's water problem, I needed this holistic way. And consumers were actually constantly switching between sources. They were kind of saying, if I don't get this, I'm going to get this. If I don't get this, I'm going to get this, right? And so if I don't have ways or frameworks, and this again involved a whole bunch of how do I look at consumer behavior? How do I understand how consumers switch between sources? How do I understand if I invest in keeping the groundwater system filled, will that allow me to displace what I was going to get from the pipe supply system? How do I do that? So anyway, that was the long and short of it. I can't show you my entire consumption model, but this is kind of the kinds of models. We did a whole bunch of data collection to ask all of these questions about how do these guys switch, how do these guys source, you know, what happens with the water utility, what happens when the reservoir dries. You ask all of those questions, find the patterns in each of them, and then you pull it all together in a model. So then we ran it, and then we put it into the future. But long and short of it is that the reservoir went dry because Chennai doesn't have reservoir capacity. And that's not even changed even today. That remains, which is why you hear Chennai talking much more about getting water from Mettur and trying to get access to larger storage. Because the reservoir capacity was low, the reservoir was bone dry for that year. And so it wasn't enough water to put into a pipe supply system, which is why the pipe supply system shut down. And then what happened as consumers then started not getting pipe supply, they started pumping the heck out of groundwater. One important insight from this work was that the reason the aquifer dried was not only because people were pumping more, but because there was pipeline leakage in Chennai, but in Bangalore as well, contributes to 50% of the recharge of urban aquifers. And so if your pipelines, then if you shut down your pipe system, suddenly all your recharge has gone away. And so the aquifer dried not only because people were pumping, but also that leaky pipeline recharge it was dependent on had disappeared. And so then suddenly you had this huge increase in the number of wells that went dry, and then consumers became tanker dependent. So this is the third thing, and I'm really running short of time, I think. So Jagdish was very kind to give me these slides, but long and short of it was that I talked about humans and water, okay, and humans, how humans modify watersheds, and that's because that is my area of expertise. But I think that it's important to understand that vegetation and plants are equally important dynamic drivers in watersheds. And specifically that when it rains, the vast majority of the water that goes into the soil comes back as evapotranspiration. So if you look at a semi-arid watershed, the kinds that we live in, a good 60% of the water never makes it to any stream or aquifer. In fact, more, even probably 70%, never makes it to any stream or aquifer. It soaks into the soil matrix and then is taken back by roots of plants and put back into the atmosphere. In India, we have virtually zero work in this area. I mean, Jagdish, why I wanted to show this is Jagdish's team is one of the few teams that has really given serious thought to understanding if we change vegetation patterns in entire watersheds, how does that alter this soaking and evapotranspiration and this recharge and infiltration and so on. And yeah, this is kind of showing you rainwater. It goes into the what we call the unsaturated zone, which is where all the roots are. And then that goes and it's taken back by vegetation, crops, trees, and so on, and goes back. And then the blue water goes into aquifers and streams and comes back out. All of our watershed, 99% of our water science is in this region. And 70% of our water is here. And this is really a huge disconnect because we're then not studying the main processes that are actually changing anything, right? And that's why I wanted to do this. This is some work which basically shows that forests and grasslands have very, very different, even for the same amount of rainfall, they evapotranspire very, very differently. And so it's really important that if we don't understand how these different vegetation systems alter our what we call the partitioning, that means if it rains 100 million liters or whatever, how much of that goes back as evapotranspiration versus stream flow versus groundwater recharge. That's what we call the partitioning of rainfall. If vegetation changes completely alter that, and in ways we don't understand, then we don't understand anything about water. And sadly in India, this is where we are. So I really wanted to put this. Jagdish's student Manish, who shortly going to defend, did very interesting work in this area where he developed instrumentation of his own and put sap flux sensors into trees. And basically what he found is that he did this work in Sikkim and he looked at various kinds of vegetation. And he found that even two broad-leafed temperate tree species, which you expect to be similar in many ways, had completely different rates of evapotranspiration. And that means that we've measured, a handful of these in the country. And what we need to do is this times 1,000 before we really start understanding what our vegetation water dynamics is. And basically then they did a ton of work saying, we've all heard that forests are sponges, yet when we saw that earlier graph of forests to grasslands, we found forests actually evapotranspire a lot more for the same amount of water. So are forests good or bad? Well, the answer is very complex, and it basically depends on a bunch of things in terms of what the forest cover is, as well as the dry season stream flows, and in different types of systems, different types of trade-offs dominate. The other piece of work, that work is only beginning in India, and this goes back to the question of do forests bring rain or not. If you only study the forests and the root zone and the sap flux and so on, you don't understand the regional cycling of moisture that forests bring. And some work, which is very, very recent, is basically showing, you can see just 2018, work from IIT Bombay actually, this one, which shows that the Western Ghats basically possibly supply, bring in rainfall into Tamil Nadu. And so therefore deforestation upstream can change rainfall patterns downstream. Now, we don't have any understanding of this stuff. Even this is based on a modeling study. In order to piece all these pieces of evidence together, which is to say, what makes a difference? Is there a size of forest patch? Is there a type of forest that makes a difference? And so on. We're not anywhere close to answering any of those questions. We're so far away. And so I just wanted to put that there. So the long and short of it, and this is my last slide, which is basically we need a lot of water science, but we need very different type of water science than what we've done before. All of the three cases that I gave you, which is 2 of them were mine and 1 of them from Jagdish's group, required work that is field-driven, that is taking measurements. And our work at least is problem-driven because we are a application-oriented scientific institution. So it's very problem-driven. But the minute you say that I want to do problem-driven science, the world is messy, and therefore science is messy. And it requires you to be interdisciplinary, transdisciplinary, multidisciplinary. It requires you to not think of science as something you do in silos, individually sitting in your lab late at night, but really about collaborative teams, which requires completely different ways of doing science. And it requires science that involves being grounded, talking to people, not being disdainful of people that are trained differently from you. And that requires conversations and training and structures, both institutional structures as well as funding structures, which are very different from what we have today. So I really hope that many of you will take these problems to heart and take science in very different ways than we've historically engaged with it. And then we'll actually be able to solve some problems. Thank you. I'm Veena Srinivasan. Thank you so much for inviting me to this lecture series on submerged lecture series on water. It was a really fascinating experience today because firstly, young people, lots of enthusiasm from the young people, and they asked really interesting and very, I think, sharp questions on what is science, how do we do the right kind of science, what will build the, how do we get there, what's going to build the skills. And then on the content itself, I mean, they came prepared, they had read, they kind of were asked, spoke intelligently. So I think firstly I wanted to compliment the Bangalore Science Gallery for this whole endeavor, because I think that it's very needed in India, especially where we think about education and science as being something that we do till the 12th standard, and then that gets us past the 12th grade, and then gets us our degree, and then it gets us a job. And it's not something that is part of our everyday life or part of our everyday conversation.